Here we have an example. A certain gasoline engine has an efficiency of 30%. What would the hot reservoir temperature be for a Carnot engine having that efficiency, if it operates with a cold reservoir temperature of 200 degrees Celsius? We recall the expression for efficiency for heat engines, shown here in equation 6. We rewrite this in terms of temperatures and convert the temperature to Kelvin scale. We see that the temperature of the hot reservoir is about 676 Kelvin or 403 degrees Celsius for a gasoline engine with 30% efficiency. Heat engines follow conservation energy according to the first law of thermodynamics. The second law sets the limit on how efficient a heat engine can be, which can never be 100%. Based on the conservation of energy of a heat engine, its internal energy is equal to zero. Heat engine follows a cyclic process which is due to the conservedness of its energy. Here we have a typical pressure volume diagram of a heat engine where it follows a cyclic process. Process 1 to 2, which is at constant volume, heat enters the system. Process 2 to 3, work is done by the gas adiabatically. Process 3 to 4, heat leaves the system into the environment, and process 4 to 1, work is done on the gas. An Otto cycle is an idealized thermodynamic cycle that is commonly used in automobiles. The system begins with process A to B, which is an adiabatic compression of gas and ignited at point B. Then at process B to C, heat is produced by the ignition of gasoline in an isochoric process or constant volume. After that it proceeds to process C to D, which is again an adiabatic process but for expansion of the piston engine. Then finally it goes to process D to A, where heat is released into the environment in an isochoric process. Here we have a simulated image of a piston for an Otto cycle as mentioned in the previous slides. You can see how the fuel is compressed and ignited to create the motion of motor vehicles. We see how the state changes as the piston moves along its cycle from taking on the fuel and air mixture by intake process, where the volume increases, then pressing it the next stage and pushing the piston into a cycle of continuous motion. Let us look at the isochoric processes where heat enters or QH and the heat leaves or QC. We recall that both process B to C and D to A are isochoric processes or constant volume. So the equation that describes the heat entering and leaving is given by equation 7 and equation 8. Note that the molar heat capacity is given for constant volume condition. Here we see the details of the energy process for an Otto cycle as functions for work, heat, and internal energy. We see the process start with an adiabatic compression from state A to state B. Then it is followed by the isochoric process from state B to state C. Then after that is the adiabatic expansion from point C to point D. And the final process, which is the isochoric process from state D back to state A. Here we have another type of cycle system, which is the Carnot cycle. It is an ideal reversible thermodynamic cycle and it is described as a perfect engine. The system is initiated at process A to B, where the gas expands isothermally at temperature TH, absorbing heat QH. It then proceeds to process B to C, where it expands adiabatically until its temperature drops to TC. After that it goes to process C to D, where it compresses isothermally expelling heat QC at temperature TC. Finally it then goes back to process D to A, where it compresses adiabatically back to its original state. Here summarize the work, heat, and internal energy for the Carnot cycle. We see the work, heat, and internal energy equations for the different processes. The process starts with an isothermal expansion from state A to state B. Then followed by an adiabatic expansion from state B to state C. Next is an isothermal compression from state C to state D. Finally, it is followed by an adiabatic compression where it goes back from state D to state A. Here we have the comparison of the efficiencies for two different types of engine. The Carnot cycle efficiency is given by equation 6 and for the Otto cycle it is given by equation 9. Here the Otto cycle efficiency is dependent on the compression ratio of the engine. The compression ratio is the ratio of the maximum volume over the minimum volume a cycle can achieve. The ideal Otto cycle has a compression ratio of 8:1 of its maximum and minimum volume.